Well, sounds cool. I've recorded a meeting before. Do you think you want to start, Kaushik?
Yeah, probably good.
Okay, let me pull up the slides. Here we go. And let me see.
How many people said they could make this time again? Like 7?
I think so, but that included me.
Okay.
Let me see. Can you see my screen?
No, can't see it right now.
Okay, can you see it?
Yeah, it's in the non-presented mode. And now
What
it's
about
okay.
now? Okay. Well, let me pull up the speaker notes. Wait. Yeah, how do I see chat? Oh, okay, there. Let's see. Okay. Yeah. So let's start. All right, Kaushik, you're on the first slide.
Oh yeah. Okay. So these are the main topics that we're going to cover this like GA. It's kind of just going to be a review of AI/ML. So the 3 main categories that we're going to go into are ML and its components. There we'll cover the different types of machine learning, what features and labels are, what the different difference between regression and classification models, what hyperparameters are, bias, variance, and epochs, which is also another thing we'll actually get into, and the loss and loss function for evaluating your model. Then further like to increase your model performance, there's like different things like watching out for overfitting and underfitting, regularization, measuring the model performance. That's something you do through a confusion matrix, which we have a lot more about later. And we'll also go into handling data where we'll cover all these different topics that we've listed here. We'll just start with going into directly like what machine learning is and overview.
Yeah. Okay, so three main components to machine learning are data, features, and algorithms, right? And so for the example that I'm going to use here that I'm going to like continue using is for house price prediction. So like say that you know, like you're working for, I don't know, for UNT or whatever, and they want you to build a model that can predict the price of a house, right? So um, yeah, I mean, yeah, that's just what we're gonna run with. So the first part is data, and so data is just exactly what you think, right? It's data, and there's all different types of data, and we're not talking about programming data types like integer, boolean, whatever. We mean like you know, like relationally different types of data. So like it can be images, text, it could just be collections of numbers, it could be audio, right? And it's important for you to know exactly what type of data it is, or if you don't know, then for you to take note that you don't know, you know, what the data you're working with is, um, because the type of data that you use heavily affects the accuracy of your model and whether or not your model can actually use the data. Um, because there's a lot of different machine learning models that are made for a lot of different tasks. And a big factor to take into consideration when picking your model based on your data is not only the relationship, like I said before, like for example, images, right? Um, that is basically made up of a bunch of pixel values, which are related spatially, right? With an actual like XY coordinate grid, right? Like a pixel right above another would be is more likely to be similar to that pixel than you know, another pixel that's, I don't know, across the on the other side of the image. So basically, and like another example is audio. Like that's sequential data. Uh, you know, that goes. You know, if you've ever, I don't. Wait, can you see? I think I need to change my screen. Here we go. Can you see this?
Yeah, we can see it.
Okay. So like audio, on the other hand, you know, it's like a waveform, right? So instead of being related spatially, it's related temporally, where, you know, audio right here, it might give more clues about audio that's more nearby in time, like this section, than over here, right? So, you know, that's another example. And then, so there's different types of models that are optimized for different types of data. And on top of that, there's also different levels of complexity for the models. And so when you're picking a model, it has to match the complexity of what you think the pattern could be in the data. And so if you have like a data set where, for example, it's a very simple relationship, right? You think that one variable is based on another just linearly, then you might want to pick a much simpler model to be able to pick up on that pattern than a more complex one. Uh, you know, because it might not. Well, we'll get into that, the specifics of that later. But yeah, just know that the complexity of the model is important. That it matches what the pattern you think is going to be. And so you can collect data with the, you know, there's a lot of different ways you can collect data. Whether like you send out a survey, or you collect user data from somewhere, or wherever, like you find a data set online. But you also have to know what the reliability of your data is, right? So because what you want from your data when you're collecting it is to have a good representative sample of what your model might encounter in the real world. Because you want to prepare it for what it might encounter when it's actually in use. And so if you can find a good data set that it's across a broad spectrum of what you might think it could encounter, and then that's good. That's what you want, so that if your model ever encounters something that may be like out of the ordinary, it's more likely that it's found something similar in the data set and could use what it's learned better and be more accurate in those edge cases. And so um, on the other end of on the other hand, if you don't have reliable data or representative data, so if, like, for example, UNT tells you to find house prices of any dwelling, including like apartments and mansions, from anywhere in the United States, right? They want you to be able to predict. Then just using, for example, like a Denton suburban housing report from 2017, just using that data set is not good data. It's like garbage in relation to what you actually want your model to be able to do, right? Because that's a very small, it's not representative of everything it may encounter. That's a small subset of all houses, right? Because, there's a lot of different factors to take into account. And by just taking, suburban houses in Denton in 2017, um, that doesn't show a lot of variance in those factors that you might want to take into account. So, like, for example, you probably want data that includes like apartment data, one-story home, two-story home, mansions, urban, suburban, rural, across everything that you might encounter. And so, yeah, so for example, let's say they give you this, Denton suburban housing report from 2017. So then you should only expect your model to be able to, predict house prices, within suburban housing, right? Because, a house that may cost 150,000 in Denton may cost 400,000 in San Francisco. And so, yeah, on that end, you also want to take location into consideration. And so, yeah, that's pretty much everything about data. So the next thing is features and labels. And so basically when you get your data, right, it's typically in the form of a CSV, or you want to turn it into a CSV, which stands for comma separated values. And it's basically a table just like this one, right? And the way that CSVs are organized is that the columns, right, are features. And so those are describe properties of each individual data point. So for this CSV, right, the features size and edge, those are attributes of whatever this may be describing. I don't know, say it's like a car, right? So a car size and a car edge. I don't know what that means, but I'll just go with it. And so these features, they describe the properties of each data point in your data set. And each row is an individual data point in your data set. So this would be small dotted green. This would be one car, right? And then the next car would be big striped in yellow. The next car would be medium, normal, and green. And so features are basically what your machine learning algorithm uses, the information it takes in, to be able to predict a label, which is the output. And so, when you see features are the input, labels are the output, you think your feature should probably be indicative of what the output is, right? There should be some sort of correlation, right? So, for example, if you're trying to predict like how likely someone is to get lung cancer, right? An important feature would probably be whether they smoke or not. And so it's also important to take into consideration what you might think the relationship is between the features and the labels. Because say like you're trying to predict house prices, right? And in your data set, you could have all these features, that include things like address, square feet or square footage, what year it was built in, how many bedrooms, how many bathrooms, stuff like that. Now you could have all those attributes as features, right? So like one house would have 3 bath, 2 bedroom, 1,500 square feet, whatever, whatever. And so the label for that would be the price, because that's what you're trying to predict. That's what you're trying to have the model output. But what if your data set, on top of all that information about the house, it also included something like hair color of the last owner of the house, right? So like, I don't know, blonde, brown, black, whatever. So that feature in particular, um, just by your own guess, just by your hypothesis, your educated guess, you would think that that doesn't really have an effect on the output label, right? The hair color of the last owner of the house. And it doesn't just have to be a guess either. Like if you're doing something with biology, for example, and you're like, you experimentally proved that a particular hormone has nothing to do with a certain response or whatever, right? Then you might suspect that there's no correlation between those two. And so including that extra feature may actually damage the accuracy of the model, because it may pick up on arbitrary patterns in that extra uh, useless feature that aren't actually real patterns. It just happen to be, happens to show up as a pattern even though it's not. And so um, this is another part of machine learning, which is feature selection, which is basically what it sounds like: selecting which features you want to include in your machine learning model. Which ones do you think it should take into consideration? And so, as an extension of that, there's also feature engineering, where you can modify your existing features or add new ones. But we'll get into that later. But yeah, the point is that it's important to select your features carefully. And the last thing is that labels, that's what the data is labeled as, right? So like this car, which is small and dotted, is labeled as green. This one's labeled as yellow. This is labeled as green. So for this example, you'd be trying to predict the color. But labels, although here there's only one label and multiple features, there can actually be multiple labels depending on what your machine learning model, how you use it and what, because say like, for example, for your house prices, right? You want it to predict not only, I don't know, like prices, but you also want it to predict like an estimated impact on neighboring house values or something like that, right? Then you could have multiple labels and you could train different machine learning models to predict these two different things. And so labels aren't necessarily, they're not set in stone. You can pick different columns of the data set if you think they can be predicted properly given the other features, right? And then along this same train of thought, you can also decide not to use any labels at all, right? And so if you have no labels, then the question is like, well, then what do you do? What do you try to predict if you don't know what the outcome is, right? So if you know that a house has 2 stories, 3 bath, 2 bedroom, whatever, that's not useful if you don't know what the final price of the house is. It doesn't help your model train. And so in these cases where you have unlabeled data or you don't use the labels, is another type of machine learning called unsupervised learning, which we'll get into later. But yeah, so labeled data is supervised and unlabeled is unsupervised. And so the last component, I guess, would be algorithms. And so these are actually like the hearts of the models, right? Like the brain behind it all. What you actually train and what you use once you're done training. What gives like accurate outputs, right? And so, like I said earlier, there's different types of models with varying levels of complexity that also that work differently for different tasks. And so one model might be good for really simple classification, if you think there's like a simple relationship, a simple pattern in your data, then you might want to use something simpler like a small decision tree or logistic regression. Or if you think that there's a much more complex relationship in your data, um, then you might want to use something more complicated, like an ensemble method or neural network. And beyond complexity, like I also said earlier, there's different models that are good for different types of data. So sequential data could be handled differently by a certain model than like image data or video data, right? And so um, it's important to also take into consideration these things when picking your algorithms. And on top of that, uh, I also mentioned earlier how there's unsupervised and supervised learning. There's different algorithms that do those two. So you can't use an unsupervised learning method if you want to do supervised learning. And, they also give different types of outputs. And so if you want, certain, well, I basically already said this, like certain outputs, and you pick that type of model. And so, this might be, I found this image online, but it shows like the factors you may take into consideration when picking your model. And so there's some that are good, that work fairly well with very few samples. Others that maybe, require more samples to be accurate. Others that, this would be unsupervised learning. This section, I don't know if you can see my mouse, but this clustering blob, this would be unsupervised learning, as well as this dimensionality reduction blob. And so there's a lot of different, all these things are, you should take into consideration when picking your model. And so, okay, this is Kaushik's slide now.
So now we're just going to go into like the different types of machine learning. So the two main ones are regression and classification. So regression is what the difference between both of these is what they output really. Regression, you're usually trying to predict a certain value. It could be like given, the input of a bunch of people's ages and heights, then your model could be some sort of simple predictor that literally just, depending on the age, gives you their possible height. That's a really bad model. You're probably never gonna need it, but that's a simple example of regression. Classification, on the other hand, could be something like based off of I guess certain images, you can classify whether they're a dog or a cat. It's usually categorical, and the biggest difference is not going to be like with inputs, because you can input like the same data to different to a regression model and a classification model and get different outputs as well. So it's not too complicated when it comes to figuring out how you're gonna set up your input and all that.
Yeah, and classification isn't just limited to binary classification. It's either cold or hot, one or the other. You can also have multi-class. We have more than just two classes where it could predict it's cold, warm, hot, right? Or however many classes that you want.
Okay, so the main three realms of machine learning are supervised, unsupervised, and reinforcement learning. So supervised learning is when you have labels. It's basically data that you're telling the model, this set of data belongs to this. Let's say we're using categories, right? If you have pictures that are labeled cat, dog, and cow or whatever, right? And you literally you give the picture and it's labeled as in a folder or cow or something, and so you're telling the model this is a cow. Then you're telling this model this is a cat and this is a dog. With unsupervised learning, you're just giving it the pictures, a lot of pictures. Henry, it's sharing the whole thing.
Oh, it is? Whoops, my bad.
Okay, so with unsupervised, you can give it the same data set without labels, and based off of the features that it recognizes, it'll split it into its own groups. And it's just a matter of whether you provide a label or not for your data. And with reinforcement learning, it's a completely different approach from those. Reinforcement learning is usually about learning as you go. Reinforcement learning models, like one that I specifically have worked with, is like games, right? As a model plays a game, it learns to make better decisions based off of the different the makes and the score it gets from each of those moves. So it's just these are the three main realms of machine learning. We'll kind of get into it a bit more too later.
Yeah, and so we're just gonna use this as an example model. We're just gonna, give a basic overview of this. We'll go more in depth over this next time. But yeah, for now, we're just gonna use this as an example model to apply our other concepts that we're gonna learn. And so linear regression, if you remember what regression is, it's basically predicting a numerical value. A range, the range is from like 0 to 1 instead of, classification where you can only pick 0 or 1, right? And so the inputs are also continuous. And basically, if you ever use like Microsoft Excel or Google Sheets, like trend line, you've probably used linear regression before then, because linear regression basically finds the line of best fit, right? And so if like given x is like 50, right, then it's saying, oh, then y is most likely to be 0, since that sort of falls in the line. And so and it predicts that based on all this existing data, right, that you trained it on. And so for example, like say you have your house prices data set and you want to predict the house price only from square footage, right? Obviously, that's like an oversimplification. But I mean, that's just what we're going to use for now, just so we can use a simple model, right? So like square footage is 1,000, then house price is like 120,000. Square footage is 2,500, then house price is 350,000, whatever. Right, and so that would be kind of be the output of what the house price model based on that would be.
So when it comes to machine learning models in general, there's the way that you measure its performance is through something called measuring loss, and you do that with loss functions. Loss is essentially a metric. It tells you the model's performance after an epoch. An epoch is a certain training cycle. When a model has data and it's learning off of that data, it doesn't just read through it once, it reads through it multiple times, making adjustments as it goes in order to improve its understanding of the data and its prediction abilities. So loss, there's a bunch of ways to measure that. And the biggest there's loss functions are like what you provide. It's what outputs the loss, right? You basically get the loss from these functions, and these functions are defined as it could be something simple like your percent difference, right? How much what the actual height should have been versus what height you were given. And then once you have that error, it was a form of loss, you can basically tell the model, hey, the loss on this is extremely high. You have to keep training or something like that. And I guess it's not like you tell it you have to keep training. It's just when you as a person are viewing this model, you can say, hey, at this point the loss was like 30% inaccurate or something, and then or 30% accuracy, and then later on the accuracy went up to like 80%. That means your loss went down. So as you continue to train, of course, your model gets better and better, but it also, comes into problems if you overtrain it. And that we'll get into a little later. That's called overfitting. And underfitting, which is the opposite of overfitting, is when you simply don't train the model enough, so it's overgeneralizing based off of the data. It's like if it was supposed to be, quadratic regression of some sort, it just draws a straight line. That's like, not fitting to the actual curve. But we'll get into that later. And some common loss metrics would be like mean squared error. That's a certain way that you can decide how accurate your model is. Your mean squared error would go down over time, right? Because as your model gets better, your error goes down. The reason why you would square it in that case is because if you have an error that's really big, squaring it makes it even bigger. But if you have an error that's small, squaring it would make it bigger, but not as big as the other one. So that's like, there's just a bunch of different approaches in it in doing so. Mean squared error is basically, it takes, that's the metric that you use. It's a mean because it's, you literally take the loss of over multiple epochs and you you average it out at the end. So it's just a way to figure out if your model is improving or not.
Yeah, and so for example, I can hear myself. Like here, like say this is data, right? And so when your model first trains, it just might come up with a line like this, right? And so the way that mean squared error, for example, that's a common loss function. The way it works is, so first of all, how would you know how close this is to fitting the line to the actual? Because the actual line would be something like this, right? And so if you had something like this, how would a computer be able to tell that is not close to the line at all? Because I can't look at it visually; it has the numbers.
Are you showing something?
Oh yeah. Wait, is it not showing?
No, I think you just shared the presentation.
Okay. Oh, I might have been doing it. There we go. Yeah. So say this is your function, right, or your data, and this is the line it draws, and so you can see it visually and tell that it's like completely off, but a machine only has the numbers, right? And so a way that you could tell how far it was off is by just taking the difference between what it predicted and what the actual value is for each value, right? So for the first one, the actual value is here, and the predicted was here, right? And so you can see there's a very large gap here. Um, this is a big difference in what the actual is and the predicted. And the reason that's used as a metric is because if you decrease the difference between the actual data and your predicted data, that means your predictions are getting closer to the truth, right? Closer to what the actual data is. And so you see this one's big, this one's also big. This is all very large loss values, right? And so a mean average loss function, a mean absolute loss function, right? It's called that's a bad M. MAE. This basically takes the absolute value of all these differences and adds them up, right? And then divides it by however many, which is just the mean. So the mean absolute loss here would be like, say this is like 5, whatever. Right? Say it was like 4 or something. Right? That'd just be taking the average of all these. And so that's one that can be used. That's pretty common, but another common one is mean squared error instead of mean absolute error. And so, this may give an error of 4, but a mean squared error, right? This loss function, instead of taking what's it called, the absolute value of them, it takes the squared value, right? So instead of this just being 5, it would be 25, which is like really big error value. And then this one would also be huge. And so the reason why you might want to choose mean squared error over mean absolute error is because mean squared error is better at prioritizing getting close, relatively close to the truth. Because let me give a different example to show the difference.
It punishes like outliers really badly.
Yeah, it does. And there's different loss functions for outliers and stuff like that.
Mm-hmm.
But say your data was like something like that, right? And so the line of best fit in reality would be like this, right? But if you're using mean average error, then a line that looks like this would be no different from a line that looks like this. And those are both obviously, they're pretty close, but they're not the best. And the reason is because, well, you just take the error. So this is large. Uh, all these are large, and then the ones that it's close to have basically no error, right? And then if you take the top one, something like this, right? These would have basically no error, and then it'd have the same effect, but except the bottom ones are the one with large error. And so, um, when you have mean average error, it might get close, and it will try to reduce error and get some of them to zero, but it won't try to get like the average, like the middle between them, right? That's where mean squared error steps in, because if you have something like this, then this becomes much larger under mean squared error because of it's squared. On the other hand, if you have something like this in the middle, which is the closest, then mean squared error, this is where it has the lowest loss, right? Because even though they're pretty large, they're not as large, and like it has more errors, but all the most of the errors that it adds are relatively small, right? So it's like saying, for MAE, right? Like say we're talking about these two error values, it'd be having like, if you were here, then it might be saying like, oh, your loss is 0 plus 4, right? It's low. But for mean squared, if you're closer to 1 than the other, then it'd be like, oh, you're 0 plus 16. That's really high. And on the other hand, if you're in the middle, right, you're 2 away from each, then it'd be like 2 squared. Right? Oh, you're only 8 away as opposed to 16. So therefore, the middle is the closest, right? And so, yeah, just in general, just remember that mean squared error is better for getting like the middle and making every single loss relatively small. And mean absolute error um, makes doesn't particularly prioritize a singular middle. Instead, it most likely brings some some of the errors to zero, and some of the ones may be high, right? And that's just as a result of what the loss function is. And so this is what I was talking about earlier with complexity. And so these bias and variance are two sources of errors in models, right, that arise from complexity. And so bias is basically the assumptions made by the algorithm, right? And so an algorithm with high bias would be one that's a lot simpler, right? So like linear regression, the bias there is that it assumes that that the relationship is linear in nature, right? And so like I said earlier, you should match the complexity of your patterns of what you think the pattern will be with the complexity of the model. And so if you have a data set with what you think to be a linear relationship, then this would be for the left on the graph. And so because the assumption made by the bias is correct. And then on the other hand, variance is basically sensitivity to the input data. So if your input data changes a little bit, then it may change a lot in the output of your model. And so that's the other end of the spectrum, where more variance means more complexity. And you know, say your data set has a much more complicated relationship, like house prices, for example. I know that we're using linear regression, but like I said earlier, in a real life situation, this would be the wrong choice because it oversimplifies, right? It assumes that the relationship is linear between the square footage and the price, when in reality, there's a lot of other factors to take into account. And so for house prices, you might want to model with a lot of variance instead, because you want it to be able to take all these things into account, right? You want to say, oh, if your model is in this, you know, if your model is in this high class neighborhood, if your house is in this high class neighborhood, as opposed to a low class neighborhood that's like 1,000 feet away, right? You want that to change a lot, change your output a lot, right? As it would in real life. And so, yeah, this basically captures what the the balance you want to find between variance and bias and the complexity of your models. And so, yeah, like it says here, high bias can a model with high bias can ignore things about a data set that may be important factors, and high variance could cause a model to pick up on random patterns that it thinks are legitimate, right, and cause a error there.
So when it comes to like training your model, right? There's two things to like watch out for: overfitting and underfitting. Overfitting, that's when you like overtrain the model. That's like overfitting. So it's basically like if you look at the figure in the bottom right, you see how it's like not generalizing enough. Instead, it's specifying to the training data that you passed it. This happens when you have the model go through too many training cycles or have too many epochs essentially. And this, like relating it to the last slide, means there's a high variance. So if you were to put data that's not in the training like set, it would like vary a lot from. It's just not going to be very accurate, but it has a low bias. So you know this means that you don't have a good balance between variance and bias, because your high variance outweighs the important like the benefits of having a lower bias. And usually when you're preventing overfitting, you have to check your training data error and your validation data error. We'll get into the different types of data later, and how you should be splitting up your data to training, validation, and test data. But one specific like form of that is regularization, which is also covered later on in the slide. And essentially, overfitting is kind of making the model give into background noise. It's like it's making it so that your model is making correlations between things that should not exist. Underfitting, which is the complete opposite, is when your model is overgeneralizing. It's not trained enough. Usually you see that it's when your error is super high, or whatever you're using to measure the loss function. And so that has a high bias and a low variance, which, you know, again, is a bad trade-off. You don't want like an extremely high bias when even if your variance is low. And to prevent it, you just have to normally like look for the high losses in the training data or during your epochs. Basically, after each epoch, you have a summary of how like the model metrics, and based off of that, you should be able to understand if your model is getting more accurate or not, or if it still needs to train a bit more. And in addition to looking for the high loss, once you do find it, and you like increase the amount of training, and it doesn't end up working out, you could also just end up looking for better data. It might not be a problem with your model, it might be a problem with your data itself. Like Henry gave an example earlier about how you could be trying to predict house prices across the entirety of the US, but your data is only conformed to Denton suburbs. Regardless of how good your model is, you're not going to be that accurate because there's so many more like different conditions that have to be satisfied. And even though you don't need to know those conditions, you should have data for houses in each of these individual conditions. And that that's just not something you can change with the number of epochs that you put your model through. Okay, so I can go over hyperparameters.
Wait, I'm here. I'm here.
You wanna go for it?
It's my label is mine on the slides.
Go for it.
Yeah, so basically, hyperparameters are high-level model parameters. Oh, actually, I don't think that's the best wording. Wait. I don't know, because model parameters is its own thing. But basically, they're high-level model parameters, right? And these are things that affect how the model trains, right? And so the model itself is made up of parameters, right? Model parameters. So, for example, for a linear regression, that would be like the slope and the slope and the y-intercept. And so those are model parameters that affect what the model's predict accuracy is, and those are optimized by the model. And so those are the things that the model changes as it's training to be able to better predict the output from the input, right? But hyperparameters, on the other hand, are they're parameters about the model itself, about how it learns, right? So, for example, like for linear regression, let me pull up another page. Here you go. Right. So say your model. Right, this is the data, and your model's initial guess is this, right? And so the model sees the model could see what the error is, right? And in what direction it should move it. It should rotate the slope. And a parameter of this, this is a parameter, a hyperparameter, right? How much it should move the line whenever it's trying to adjust to the slope, right? So if you have like this is called learning rate. So if you have a high learning rate, then it might overshoot and do like this. If you have a low learning rate, then it might only slightly adjust, right? And the model ends up being more accurate, but at the cost of time, because it takes a lot more epochs and time to train it to be accurate. And so, yeah, hyperparameters are just these I can't read that part, but the Wikipedia definition states it well, which is a parameter whose value is used to control the learning process, right? And so there's several different ways to optimize these hyperparameters so that your model is as accurate as possible. There's like grid search, random search, gradient based, but we'll probably go over those in another meeting. How to fine tune your hyperparameters. But yeah, this in and of itself is a pretty big part of machine learning. If you have enough experience, then you have an idea of what your hyperparameters should be for your model. And so the next topic is regularization. And we'll just sort of do an overview of this. But basically, it's a method to reduce overfitting in models. And so and you can see this transparent background PNG. For example, these red points are the training data, right? And the blue line, or the dark blue line, might be what a overfit model may predict to be the relationship here, right? And you can see clearly that it's very overfit, right? It has all these like random variances. It's not smooth at all and doesn't capture the pattern well. And so the way that model regularization works is that it seeks to reduce the model parameters that introduce variance into the output of the model. So for linear regression, for example, you know, it has, well, the model parameters for those for simple linear regression are basically just the y-intercept and the slope. And so it's already pretty simple, but if you were to apply regularization to it, you could apply it to the slope, where if you don't want it to be overly sensitive to input data, you could apply it to the slope and encourage it to be to have a lower value, right? You encourage the output to be more flat, right? And so instead of having a prediction curve like this, it could predict something closer to this, right? And so the way you usually do that to you achieve regularization and reducing the parameters that introduce variance in a model is by adding it to the loss function. And so here, instead of the loss function being the distance between all the data points, you could calculate, distance, whatever. You could also add the slope into it as well, right? So instead of like 0.1 squared plus whatever, you could also add an extra term for like, I don't know, slope, right? Equals the error, right? And so once you add this into your loss function, that means your model not only optimizes its accuracies to the data set, to the training data. You also get the model to optimize its own parameters. Okay, I need to block my friend real quick. Hold up. Actually, no, that's fine. You can read those. But yeah, so this is how you typically achieve regularization, right? And so, yeah, so the next part is going to be about handling data. It's going to be more an overview of data science introductory principles. And so like I talked about earlier, there's a lot of different data types. And so, numerical, where you have, this would be like a house price output. It could be worth this much money. Categorical, this is where your data is labeled in categories. So like, say you have, you're trying to classify an image, right? And you have images of animals, right? And so the categories for that could be like cat, dog, bird, fish, right? And so you have those 4 types of images. You have pictures of cats, pictures of dogs, pictures of birds, pictures of fish. And your labeled output would be the category. So label, it could be like a string that says cat, a string that says dog, string that says bird, or it could just be like a number that represents what it could be. So like 0 is cat, 1 is dog, 2 is bird, etc. And then, the same thing here. So like if you had a picture of devices, you could have it labeled as being a desktop, laptop, mobile, whatever, right? And so like I said earlier, the relationship between data must be taken into consideration. And so, we have images, sequences, and other data where you might not know what the relationship is. There are models that cover, data where you don't know what the relationship is. And so here, if any of you know what a spectrogram is, I think it's spectrograph. Let me see. I know a spectrogram. Okay. A spectrogram is basically a visual representation of audio, right? Where this represents frequency, and then this is time, right? So you can see here at 0.1 or whatever, 0.1, there was some audio up in the higher frequency and then a lot of audio down in the lower frequency, not much in the middle. And so this is a way to be able to represent audio data in a visual format, which you can then use, you can use other types of machine learning models, right? because normally, like an image model, for example, wouldn't be able to work on audio data, like raw audio data. But when you transform your data into this, then you can do it. This is a part of feature engineering. And so another important part of data science and features engineering is feature scaling. And so feature scaling is basically taking all your numerical features, right? So not categorical, right? This is only numerical, and then scaling them down to all be within the same range or the same like ballpark, right? And so why would you do this? Well, a lot of models use gradient descent-based methods, and there's also models that use distance-based methods, and these are heavily influenced by the actual values of the data itself, right? So if like say that you have a data set that includes it includes a student's GPA and it includes the grade in a class, right? So the GPA would be somewhere like from 0.0 to 4.0, and the class grade would be somewhere from 0 to 100, right? And so a GPA difference from 3.9 to 4.0 could be comparable to a class grade difference of like 95 to 100. But the difference here is that although they represent, 3.9 to 4.0 and 95 to 100, they represent the same thing conceptually, right? It's the same jump in like, I guess, student knowledge. They don't represent the same thing numerically, right? Because one is increasing 0.1 and another is increasing by 50 times that, by 5, right? And so these gradient descent and distance-based methods tend to give a lot more importance to the grade just because it shows much more variance, right? A feature that increases or decreases by 10 points, I think should be much more important than a feature that increases or decreases by 0.5. And so there's two main methods to do feature scaling. The first one is normalization, and it's basically just scaling your data to be from 0 to 1, right? And so if this is your data beforehand, this is what it would be after normalization, right? It's in this bounding box from 0 to 1 in both dimensions. And this is after normalizing both features of the x and y dimension. And so this is just a simple formula for scaling from lowest to highest, which is this. And so for each x value, you subtract the minimum and then divide it by maximum minus minimum. And so to break this down, the maximum minus minimum of a set, you might recognize that as the range, right? And so if the range of a set is 5, for example, you're dividing the total range by itself by 5. So for any given set, you get the range and you reduce it to 1, right? And that's what this does. And then this xi minus minimum, it just maps it to the value from 0 to 1. And so, not Notepad, Paint. Right, if you have values, like here, 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 for example, this division term, like I said, it reduces the range. So it essentially brings it down to 1, right? This is your another number line. And then this top term takes the data, say it was like, we're talking about this data point, and then it maps it in relation to the smaller range, right? So then we get the new data point would be like here, right? And then the next one would be here, down here, right? And so, and it makes sense also mathematically. So for example, the maximum, it'd be maximum minus minimum over maximum minus minimum. That scales to 1, which makes sense because it's the highest. And then the minimum would be minimum minus minimum over whatever, because this doesn't matter because this is 0, right? And so yeah, this it just scales everything from 0 to 1. Normalization, not normalization, sorry, standardization on the other hand, is the preferred method generally, because it doesn't strictly scale everything from 0 to 1. Instead, it scales everything based on its standard deviation, right? And the reason standardization is generally preferred to normalization is, say you have data like this, like, let me make another graph here. Wait, I need to make this bigger. Oh, here. Right, so your data is like this, right? And so the problem with just normalization is that your outliers here reduce the variance of your data by a lot. So then the normalized version might look like this. Right? And so what that ends up doing is that, all these points over here that should be important and taken into consideration, because of these outliers that make the range so much larger than it would be without them, it reduces them to be very similar in the end. You have this big cluster of very similar values, even though realistically, they should be uh, more separate in practice, right? The model should consider them to be further away. And so that's what standardization is for. So if you know what the equation for standard deviation is, uh, it's basically this, right? You calculate the standard deviation, um, and then you take x minus like for a given value x, you subtract the mean, and then you divide by standard deviation, right? And then that basically that scales the whole thing to be between 0 and 1. And the reason, for take the same example. So under standardization, right, where you have this big, this big group that should be important, and also these 3 outliers. Actually, let me draw this better. Instead of just being reduced to a blob like that, it would probably look more like this. Right, where more of the data is taken into consideration, right? And the effect of the outliers is lessened due to the fact that you use standard deviation instead of scaling strictly to the largest and lowest values, right? And so, well, if you don't know what the standard deviation equation is, let me search it up here. It's this basically. But yeah, if you haven't taken statistics, I know it may look complicated, but it's basically to find the distribution of how widely distributed your data is, right? So data that's a lot closer, a lot less distributed, like this, has a much lower standard deviation than data that looks more like this, right? And so that's what the standard deviation is there to account for. To scale everything relative to the distribution instead of relative to just the largest and smallest values. And so I think this is the last one we're going to go over for today, because it's already 8. Yeah, the last thing is what to do in the case of missing values, right? And this can be a common problem in data science, depending on which data you're trying to use, right? Some lesser research fields, or fields that are difficult to get data in, you may encounter this problem, right? And so this is an example, right, where like you have all this information about people, but here like the age is missing for these two, you have the experience and salary missing, missing data and a few of the features, right? And so there's a few things you can do in the case of missing data. Some models, you can just ignore the missing data, like literally just leave it in the data set and train your model anyways, because there are models that are able to work with missing data, right? But just know that you have to take that into consideration. Give a footnote that this data was not complete, model trained without a full data set, because even though it's able to work without data, um, missing data still reduces the accuracy of those models, right? Another thing you can do is drop the rows. And so if you remember, these are individual data points. So like this person, Dilip, this is one data point. Ramesh is another data point. And so what you could do is for every, if you have a model that can't handle missing data, you can go through every row and just delete every single row that has any missing data in it, right? So then we would delete Himesh, Yathisha, pretty much those two, right? And also Harika, yeah. And so the the efficacy of this depends on your data set and how much data is missing. Because if you have a lot of data missing, you can end up cutting out a lot of your data sets and severely reducing the accuracy of your model. Because if you have a data set of like 10,000 entries and then you end up cutting like 3,000, right? That's 30% of all of your data that you can no longer train with, right? And so that's a pretty big hit to your model's accuracy in the end, because it didn't have as much data to train on. Another thing you can do is to drop the columns, right? And then this suffers the same issue as the last one, right? So here, like, oh, there's missing values in age, so just delete the entire age feature, delete the experience feature, delete the position, delete the salary, right? So in this case, it would literally only leave behind the name, right? And then whatever label you want to predict, right? And so this has the same issue. Again, you should only really consider it if you have very little missing data, because you end up missing entire attributes of data points, right? And this is after feature selection, right? After you've selected features that you think should be important to the outcome, to the label, right? Cutting out those features can be severely detrimental to the performance of your model. And so the preferred method, when you have missing data, is to do something called imputation. And it sounds like a big boy machine learning word, but all it is just replacing your missing data with placeholder data. Oh, well, not placeholder data, but realistic data, right? And there's a lot of different methods of imputation. For example, mean values would literally just be taking the average of all the values and then just applying it to every single missing data, right? So like say the average of the existing data was like 26 or something, right? Then to these two, you just say, okay, just make this one 26 and make this one 26, right? Same for here, like, oh, average is 7, make this one 7. And then here, for example, you can't use mean values because it's categorical, not numerical, right? And so the equivalent of that for categories, for classification features, would be the mode instead of the mean. So the most frequent, right? So, oh, most people are 10 to 12, so just put 10 to 12 here, right? Most people here are ML engineers, put this one as ML engineer, right? And so, these are the two most basic, types of imputation. The type of imputation you do also depends on your data relationship. So for example, if you have an image, right? So your data can be like, say it's a grayscale image where black, like completely black is 0 and completely white is 1, right? So you have like 0 point whatever, right? And you have like say a couple missing pixels. Like this one is missing, right? And then you have the surrounding pixels, right? So for this, instead of just doing the mean of the entire image, right? A smarter way to do it, right, while still being easy, would be to instead just take the mean of like nearby pixels, right? So here, just take the 4 nearest pixels, or take the 8 nearest pixels, or whatever. Take the mean, or interpolate, or whatever, right? And so yeah, there's quite a few other methods like nearest neighbor, placeholder values, this thing called multivariate imputation by chain equations, or MICE, and also machine learning in and of itself. And the way machine learning, you do machine learning is say you only have missing data for age, right? And you're trying to predict salary. So for this data set, if you have missing data for age and you're trying to predict salary, you could instead train another machine learning model to take only the name, position, and experience, and then predict an age value, right? And you use your existing values as training, and then apply the machine learning model to your missing values to fill them in with values that the machine learning model you trained thinks would be realistic based on the other other existing features, right? And then once you impute it with the machine learning learned values, then you can continue using that imputed data and finally use your model to predict salary, right? That's basically what a nearest neighbor is. It's just nearest neighbor is just a specific machine learning model you use that you apply. And then the last method is imputation. Oh, this is being blocked, but imputation plus imputation flag. And basically the way that works is you do any of these methods, mean value, most frequent, placeholder, MICE, machine learning, and then you add a new feature for a new column for missing data. And all it is it's an indicator for imputed data, right? So say, age, you go through it and you find, oh, there's 2 missing data. So you create a new feature right next to data. Oh, it doesn't have to be next to data, but it's just a new feature, right? That would be like age imputation flag, right? Or age imputation indicator or something, right? And all that this would do is tell you if that particular data point has an imputed age value, right? So the imputation flag for age here would be 0, 0, 1, 1, 0, 0, 0, 0, right? Because it's only true for those ones that you imputed earlier. And this imputation flag can definitely help increase the the accuracy of your model, because it literally tells the model, oh, this age is it's imputed. So then from there your model can learn, oh, I probably shouldn't value this age value as much because it's not a real age value. And so yeah, I think that's all we're gonna do for today because it's already like 8:15. Yeah, I was just talking there for a while. Does anyone have any questions?
Also, could y'all comment your name or something, or like just text your name in chat, so that like sign in, I guess. I don't know.
Comment
Honestly,
what?
their name, but honestly,
Oh,
cool. Does anyone have any questions?
So y'all have like pd.read CSV. So when are you going to go over like actually like retrieving data and like using it like
with like actual Python libraries and stuff.
yeah.
Oh, we can go over that next week, like actually implementing all this.
Oh, okay.
But yeah, the pandas in particular. If you've ever heard of that, have you heard of that library?
Yeah.
The like the syntax and stuff for that library is very similar to R. If you've ever used that language.
Yeah. All right. Thank you.
Yeah. Yeah, that was it for today, I guess.
All right.
We'll do a lot of coding and workshops too, so
Yeah.
look out for those. All right, thanks for coming on.
Thank you.
Epoch. I don't know.
Oh my god, that's how Rhythm used to pronounce it. Remember he said epic?
Oh, right. It's an epoch.
Epic.
Epic. Yeah, our old president used to pronounce it epic, and then everyone just roasted him.
That's why he's no longer president.
Yeah, it is. What happened, Joaquin?
I yawned.
That's rude.
Oh,
You're supposed to stay attentive.
I am.
Are you though?
Yes, sir.
I got another meeting. I saw it. Which one?
Empty. Do y'all want to do like YouTube recordings of these?
This one's already being recorded.
Oh, really?
Yeah.
Oh, nice. Yeah, these are high quality.
Wait, let me
So
send.
how? Oh, what were you gonna say?
I was gonna send an image to Kaushik.
He yeeted.
How are we gonna format these? Is it gonna be like a general like GA, and then like we're gonna do like a workshop, and then a GA and a workshop?
So I think we're having lessons every week, and then like every once